All right. So welcome everybody. This is Flow seminar, where Flow stands for Federated Learning One World. And this seminar was created as a global online forum for the dissemination of latest scientific research on all aspects of federated learning. This includes, but it's not limited to, distributed optimization, learning algorithms, privacy, cryptography, personalization, system hardware, and many more. So for today's talk, it's my great pleasure to introduce you our speaker, Chandra Thapa, who received his PhD from the University of Newcastle in Australia in 2018. Currently, he's working in CSIRO Data61 in Australia as a research scientist, and prior to that, he completed his postdoc there. And in his research, he's mainly interested in privacy-preserving machine learning, adversarial machine learning, distributed system security, and network information theory. And today is he's going to tell us more about distributed machine learning framework with strict access to privacy techniques. Thank you, Chandra, for agreeing to give a talk. The floor is yours.
Thank you, Samuel, for this opportunity. Hello, everyone, and thank you for your attendance. My name is Chandra Thapa, as introduced by Samuel. So I'm from CSIRO Data61 Australia. It's a Australian National Science Agency. Today, I will be talking about parts from the 3 different works that I've done in collaboration with different collaborators. And the title for today's my presentation, I put it as the combining the federated learning and split learning, and a distributed machine learning framework and strict access control technique for the privacy and security. So it's not a single effort. So it's the effort is a joint efforts from the collaborators distributed across various organizations. There are lots from my own organization, CSIRO Data61, and from the KPMG Australia, as well as Lehigh University USA and Sungkyunkwan University, South Korea. These are the collaborators that helped me during the works that I'm presenting today with you. So this is the outline of today's my presentations. I'll quickly summarize, provide the overview about the split learning, and then I can also recall that means previously in our flow seminar, we have Pranit from MIT, and he's from the same group that proposed the split learning. And then I'll go into the Splitfed learning that we proposed, and then I will present some of our results in the evaluation of federated learning, split learning, and Splitfed learning for these IoT scenarios and use cases. And then finally, I'll conclude by discussing on our framework, that's a machine learning framework with the data analog, with the strict access control to maintain the security and privacy of the confidential data, and still perform the machine learning, including the distributed machine learning, such as federated, split, and Splitfed. So let's start with the split learning. So I'll start from the simple example of the split learning, what it is and how we perform the split learning in a very simple scenario for a neural network architecture. So we can add some layers of the neural network, and in a simplest example, we can split into the 2 parts. So if we got the neural networks as mentioned in the right-hand figure, and we split into the 2 parts. So one part, which has the initial layers, will be the client-side model person that we usually provide it to the client side. And then the remaining parts will be the server-side model person, and will compute it or train it on the server side. And why we are doing this one, I skipped the introduction of the federated learning because the flow communities are quite familiar with the federated stuff, federated learning. But the scenario, like if the computation power of the client is very low and it cannot fully run the full model like we expect in the federated learning, then these scenarios are quite useful. So the client-side model persons and the server-side model person as a whole from the full models in the split learning. And if we have a single client and a single server, what happens is single client, it forward propagates the the gradient computations. That's a forward propagation, carry the forward propagation. Then at the cot layer that we say the split layer where the model person is divided, that layer we call it cot layer. And then whatever the intermediate results or the activation functions or the outputs from that cot layer, we call it as mesh data, is passed to the server side, and then server further computes the remaining forward propagation of the model, and then it starts computing the backward propagation. Once it reaches the cot layer, then it sends back the gradients to the client, then client carries the forward backward propagation, and this completes the overall model training in the split learning setup. So now the thing is, what will happen? That means how the training happens if you have multiple clients. So in the multiple client setup and then the split learning scenario, what happens is we have the two possibilities, that if one client is engaged with the server, and the simplest example is client has the full model is divided into the two parts, split into the two parts. The initial layers will be with the client part and then the rest with the server part. So the first client engages with the server, and the server for the model training on its local data. And once it completes, the next new clients will carry on the model training with the server on its local data. But it either needs to download the data, and that means the client-side model from the the recently completed clients, that means engaged with the server to train the models, or it can actually engage with the server if the third-party trusted server or the server, if the client actually uploads the client-side model person to the server, the new client actually from the old clients. So this way we have these two scenarios like centralized distributed training. So in this case, if client 0, for an example, on the right-hand side, if it engaged with the server, it completes its training, then it uploads its client-side models to the server or the third-party server. Then client 1 as a new client to engage with the server for the training process, then it downloads the model from the server. If it is peer-to-peer distributed training, then the client 1 directly downloads the model from client-side models from the recently trained client. And it happens in round robin in the sequential manner. So that's where, that means it's a motivation for our work as well, where we question ourselves that can we somehow remove the sequential, the training process in the split learning. Because why we are asking is, if you have a number of clients, higher number of clients, then the idleness of the client side will remain there, which contributes towards the higher training time in the machine learning model developments. So that's where we are motivated and proposed a split learning. And in the split learning, I'll start it from the simple explanation of split learning. Then I'll explain a little bit more onto this. We enhance the privacy to some extent by adding few additional, integrating few additional privacy measures in the architecture level that I'll discuss in the next slide. So what happens is that it's exactly like the split learning scenario. The model is split into the simple example setup model is split into the two parts. So the first initial part will go to all the clients and that's been engaged to the server in this model development process. The remaining part will be with the main server. And all these clients, in contrast to the split learning, all these clients will compute in parallel and independently. And once they complete, they will send the activations, as this mesh data, I'd say, that's output of the cot layer, to the main server at once. And then main server carries the forward propagation, carries the backward propagation, and send the respective gradients of those activations to the associated clients. Then clients individually carries the backward propagations with respect to that gradient they shift on the main server, and they complete the back propagation. This is how it looks like the overall one epoch of the forward and backward propagation in the split learning. But at the end of each epoch, we need to somehow synchronize the models on the client side as well as server side. So that's why for the client side, we added this federated server, extra federated server to aggregate the client-side models and then synchronize the global client-side models in each of these clients. And then there will be no problem to the main server because it has all the models that is associated with each client, and then it can aggregate as its always. This federated server can be close to these clients, and then computation is not that heavy. So this is how the split-fed learning looks like. The advantage I would like to mention here is as the by default privacy advantage, as you with the federated learning or split learning, that the data never leaves the client. Another advantage of split architecture and split fashion of model training is to some extent to the model privacy as well. So if I am a model developer and I'd not like to give the full model to the main server and client to some extent, then once the training starts, client doesn't know what's the updates of the main server, and main server doesn't know what's the updates in the clients if we fulfill some sort of requirements in terms of number of layers as well as connections in the client side and the server side device accordingly. So we then try to somehow, as we know that there is communication of some data in between the clients and the main server, and then also in between the clients, that is through the global client-side models. So that's where we'll try to add a few privacy measures to prevent some of the privacy leakage that can happen, potentially happen by these activations between the client and main server, or by the the local weights that's been communicating between the clients and the Fed server. So let's start with the client and the main server part, what we did. So as again, the full model in a simple setup is split into the two portions. One portion initial layers, that portion will be the client side portion that goes to the client. But what we do is we add a noise layer. So it can be anywhere in the client side portion. So this noise layer is what it is based on. Is we designed this based on the pixel DP mechanism, where we calculate the sensitivity and then we calculate the Laplacian of the sensitivity over the privacy budget and add it to the activation vectors. So this way, whatever is input to this noise layer will be the noisy output. That means the activations of these intermediate layers, and it will be propagated throughout the rest of the layers of the neural networks. So it's quite clear that means noisy activations that will transmit through this addition of the noise layer will be more private than the non-noisy activations. And in the left-hand side, so for the client-side model synchronizations, so each clients, for each of the samples they train, they calculate the gradients. And what we did is the about this approach. That means we implemented here for the differentially private local weights just by calculating the L2 norm and then clipping it and then adding to the average gradients to make it differentially private local weights. And later on, the federated server aggregates and transmit to the clients. So wrapping up the split learning, so it's a hybrid form of federated learning and split learning. Can be considered as a better controller, right? So if it has the good part of both the federated learning as well as split learning, because as I mentioned, it has the split features because the model is split and trained. Unlike federated learning, where we need to run the full models on the client side. And then it has some features of the federated learning, where that means the clients are computing parallelly. So they don't need to be idle and wait their turn to engage with the server side to train the models on their local data set. And all the configuration that we have with the split learning, with the USAFE, sharing the labels, not sharing the labels, these are all applicable to split learning as well. We do have lots of variants of the split-fed learning. So you might have also known about this one. So these categories of the split-fed learning all based on how the main server side keeps the model that's with the associated with each of the clients. So we can start it from the figure 1, that's a figure A from our left-hand side. So in our original paper, we proposed this Splitfed version 1 and Splitfed version 2. Then in our subsequent work, we generalized this both Splitfed version, and we proposed the generalized Splitfed. And then we can study from the left-hand side, that's a Splitfed version 1. So what happens is it client sends the activations to the main server, and main server actually keeps the copies, right? Number of the copies that will be equal to the number of the clients. It's associated with its clients and carries the forward backward propagation associated with that client. And later on, once it completes the process, aggregation happens at the server for all these, for an example, 4 clients, and then it forms the server-side model. And in the client side also, it happens at the fed server. So, and then we ask the question, that means this somehow resembles the federated learning kind of scenario here. We can feel that, but we then ask, that means whether we really need to aggregate the models in the main server side path. If we assume it's a parallel computations or the definitely that has some benefits, but do we really need? So in practice, if we use the multi-thread programming or something like that, in our observation also, that not making that much of difference in between the sequential, the training the model sequentially over the activations or the smash data that is sent by clients over the keeping the copies is associated with its client. This has some advantage with the memory requirements of the server side as well. So that's why we were thinking in that direction. If you want to keep one model at the server side and keep training it, each time we'll input the activations functions or the smash data that's been passed by the client and keep continuously learning that model. So that's the Splitfed version 2, somehow more similar to the split learning scenario at the server side. And then in our generalized setup, what we did is we can have this Splitfed version 1 scenario with the some specific group of clients. And so, and then it's more, we have the flexibility to keep the number of clients within the group. And in each group, we see the sequentially trained at the server side associated with each of the smash data sent by the clients. And then later on, these groups models will be aggregated at the end of the reports. And as I mentioned, it's also because there are some concerns, like if we in these 3 scenarios that figure ABC, we share the labels with the main server, and then there will be concern that we are leaking the label to the server. And then for those concerns, we can actually have this U-step scenario where the initial few layers and the final few layers will be inside the client side, and the loss will be calculated in the client side, not in the server side, so that we don't need to steer the labels. And then we can actually have the forward backward in the U-shape as mentioned in the figures. So I'll just skip the that our evaluation and results that we presented in our original paper, where we had analyzed the 4 different image data sets. And then the key takeaway observation from that one was both our Splitfed learning version 1 and version 2 has the comparable performance to the federated learning and split learning. So I'd like to stress one more thing is we were not focused to actually outperform the federated learning, split learning, but we have somehow, that means leveraging the advantage of both the good part of federated and split and still benefit and make it beneficial for the scenarios like the resource constraint kinds in environments. Here in this presentation, so I will briefly present our, that means results that we did it for the Internet of Things scenario. This is the different work. So we analyzed on the ECG data set, which has the 5 different kinds of heartbeat rhythm signals, which is time series signal, and with the various number of clients and different data distributions as well. So the top one, the 4 figures are for the various number of clients, and it's for the IID and balanced manner. So each clients have the same number of balanced, number of samples, as well as the number of classes are all, so that means the same. So this is the performance that we observe. And then the bottom 3 figures are for the various number of clients with the imbalanced data set. So imbalance means each clients have all the classes, but they can have the various number of samples associated with each of the classes. And the key takeaway message here is split is a little bit noisy, but in this balanced or imbalanced setup, still it's outperforming the federated or the Splitfed version, Splitfed learning here in case the Splitfed version 1 to some extent in terms of convergence speed as well as the performance. So in the second data set is the speech command data set. I would say the speech command data set is the voice voice format of the MNIST data set. So it's from the 0 to 9. So it's various people's how we pronounce 0 to 9. That's a data set, a speech data set. And we analyze it again for the IID and balanced manner, as well as the imbalanced data set settings. And for the various number of clients, we see a little bit different than the ECG data set here, because ST data set has a 10 classes. So if we increase the clients, so this again, the split learning a bit noisy, as well as its convergence is faster, but with the number of rounds, that means the global epochs, its performance decreased. And we can also see that the convergence of federated learning and Splitfed is quite slow. And the another notable things we can see here is federated and the Splitfed learning are some similar, the trend of the convergence. This one is for the non-IID data distribution. So non-IID, how we create is by creating the skewness in the data distributions across all the clients. So if it is one class scenario, then each of the clients have only one class of data set. And then if it is 2, then each client have the 2 classes of data set. That's unique to that class, and it doesn't have the other clients doesn't have that data and so on, something like that. The interesting thing here in the non-ID data set of the middle column, that's for the ECG data set as well as speech command data set, the split learning, right? For the extreme non-ID scenario, that's for the one class setup, they are not converging at all. Even for the 2 and 3, it's a similar result, but for 4, somehow it converges, and then we have that result. For the federated as well as Splitfed learning, so for the non-extreme, they still manage to converge, but still they are noisy and they need lots of rounds of training to reach up to the 80% of accuracy. We also did some evaluation, that means how these machine learning models actually perform on the real devices, such as we can consider as the Raspberry Pi as a high-end IoT devices. We did some measurements on these Raspberry Pi kits by running these federated learning and Splitfed learning. So in these results, what we observe is we try to compare the split learning and Splitfed learning. In our setup, we had the 5 Raspberry Pis, and then this observation is obtained at one of the Raspberry Pis that you can think of, and we measure these overhead metrics from the time overhead, that's the training time, then communication, use memory, energy, peak power, and temperature. So I'm not going in details, that means analyzing the things, but the key trend here, the key message here is, if you think about the split and federated, so the communication or used memory or peak power and the temperature, you can see the federated learning has a bit higher than the split learning. And it's quite intuitive that why it's happening, because federated learning needs to train the full models on the Raspberry Pi compared to the split learning, because split learning, we have 2 one-dimensional convolutional layers that's been assigned to the client side to train. And then the model that we consider here is has the various architectures, right? So it can go from the 4 convolutional plus the architecture is like this one. So 4 convolutional plus 2 dense. If it is 5 conv, then it's a 5 convolutional for 2 dense. If it is 6, then it's a 6 convolutional for 2 dense, something like this way. But in the split, we always have, the clients always have the 2 one-dimensional convolution at the client side and rest on the server side. Server here in our scenario is the laptop. So we are not using the GPU and other things in this one. So as we discussed the split learning, the figure A, so split learning has a higher overhead than the federated learning, as you know, because the split learning is clients, the training happens in the sequential manner. And so do the energy, because it needs to engage with the server for a longer time period to complete the same amount of globally focused training. This is how.
Chandra.
Yep, sure.
There's one question from the audience by Anupam. Let me just try to unmute Anupam.
Hello. So I was just curious, what was the size of the model you deployed on the Raspberry Pi, given, they don't have much.
Yep. So the architecture, we tried running Mobinet and other things, but it's very hard to, so to run the full 2-dimensional, even the 2-dimensional convolutional environment. It's very hard to run on the efficiently run on the Raspberry Pi. So what we did is these models are having the 1-dimensional convolutional neural network. Right? So it starts with the 4 convolutional layers and then the 2 dense layers. Right? So it's all the convolutional layers are 1-dimensional. So they are comparatively a lower number of parameters compared to the 2-dimensionals. Yeah.
And is there a way we can simulate these low power devices instead of actually having them and deploying them? Like, is there some software simulation available?
Yeah, I heard about that. Means in the simulation environment, we can have these Raspberry Pis as well, but we haven't used actually. So we use the real devices and then the power meters to measure the power and to see the to measure these overheads. I hope I answered your question.
Yes, thank you. You did.
Thank you, Anu. So this is the other, the overhead measurements and comparing the federated split and Splitfed learning. The key trends here is we are adding the Raspberry Pis in an environment, and then if we analyze it separately, these observations, so it's quite clear. That means if we increase the number of clients, right, and then if we fix the number of total data size, then if we increase the number of clients means you divide the number of samples present in each client. So more number of clients means fewer number of samples in each of the clients. So that's why in split and Splitfed, it's communications or memory or the computations, it's decreases with the increased number of clients, because it decreases the number of samples, as well as if we fix the number of the intermediate vector size, then it's all depends on the number of samples. That's we can see it from if you go into the individual to time over rate, if you increase the number of pies, right? So it's the train, but the communication also train. But in contrast, for the federated, because it doesn't matter, the communication is all the full model, the weights, right? So it's once the model is fixed, then it doesn't matter how many clients we have or how many. So the other thing I'd like to that means stress here is these observations shows the advantage of Splitfed learning. If we see the figure B, C, D, E, that's communication, memory, peak power, and temperature. So you can see the Splitfed learning, that is Splitfed version 1, and the split learning. The performance are similar, right? So they are following the same pattern. But however, if you see the figure A, that's on the time overhead, that's a training time, the Splitfed is quite efficient than the split learning. So if we consider the 5 pi, then it's almost half, right? So this one, I'd like to enter into the third part. So it's a little bit different than the previous, our empirical analysis on the proposed, the learning algorithm. But now we are entering into the framework. So this framework is designed to, we have the product, that means which is implemented this framework. So why we designed or implemented this one is if we have the data which cannot be released due to the sensitivity of the data, sometimes the data can be highly, even illegal to process. I cannot even, as a institution or organizations, I cannot even process those data sets, or I cannot actually release those one because those can be highly distressing. So, but for the overall growth, that means the gain or the benefits, if we can do some machine learning on those models for some instance, that would be great, right? So that's why we had this NALFADA framework. The concept of NALFADA is as follows. So then we have the data consumers who would be more interested in the model development. And then for an example, they can push their models because we assume that they have the access to the metadata. They develop the models. They send it to the the data custodians, which are assumed to have some sort of computing power and engage in the computations. And they can actually get the trained models if it is okay, or they can only interested in model development and then the queries. They put some inputs and then they see the outputs if the outputs are okay to be received by the data consumers. So what we have the second part. Yep, sure.
There is another question in the chat
yep, sure.
by Yahani. Let me just quickly unmute Yahani.
Hello, Chandra.
No.
Yeah, my question is how to minimize the distance correlation between raw data point and communicated smash data in your model, like NOPIC or a split NN model, like how you reduce this distance in your model?
So, Dennis, can you repeat that question for me again?
Okay. All right, how to minimize the distance correlation between the raw data point Okay, and communicated smash data, object communicated.
Yep. The activations that smash data. Yep. So in the Splitfed, so to be honest, in this one, so we were more focused on the combining the split and federated learning scenarios, but we do have some works in the split learning scenario that is equally valid to the Splitfed as well. They try to add some loss functions at the client side, and then they try to control the activations or the leakage that can happen by measuring the correlation in between the raw data and then the smash data. That's been done by the works from the MIT. That is a few literatures that means the Pranit and his group from the MIT. They have done this work, so that's possible. So we need to somehow control by adding the some mechanisms, like the one is based on the correlation measurement, and then the loss penalties to somehow minimize the what you call the privacy leakage out of activations. So does that answer your question? Or?
Thank you very much for your answer. But leakage in the data, okay, from raw data and smash data in other clients, and how to you solve the privacy in this model? Differential privacy?
No. So in this, so in our, okay, so I'd go here. So in our scenarios, we haven't, that means explicitly measured the privacy leakage and then guarantee some privacy leakage here. So what we did exactly is we added the noise layer. So in the client side model person, so we have this noise layer added to the client side part. So it can be, we can put that one in any position, right? So it can be at the input layer, it can be at the output of these client side models, or in between somewhere there. So this is just the calibrated noise added to the activations. So it's based on the pixel TP. That's just the Laplacian noise based on the sensitivity and privacy budget.
Thank you very much. Thank you very much, Chandra. And another question.
Sure.
How you select the smashed layer in your model? Select a smashed layer.
Yep. So again, so it all depends on the scenario. That means if our client's computations is okay, then we can smash it based on the the computations requirements of the computational what you call the capacity of the clients, right? So in that scenario, if the client is fully that means having the full computation power, we can easily go with federated learning, right? So that's it, because its training time is really better than the split and the Splitfed, we know it. So, and then if it is not the case, if you want to maintain some sort of privacy in the model, some sort of the computations, it cannot fully run the full models. If we think about the deep neural networks, so it's the relevant case. So we can have that many number of layers that client can compute, right? So it is comfortable with. That's just the scenario. Yeah, I would say I can say at the moment. Yeah, but again, as you might wonder, that means what can be the best, the cut of the model to optimize the convergence or to optimize the performance. Then the honest answer is it's unclear. It all depends on that means how we analyze the scenario.
Thank you very much.
Yep. Yeah, thank you.
Yeah. Also, Chandra, can I have one quick question here?
Yeah.
Also, so with related to this noise layer. So is there actually like so for instance, like in standard DP, when you add noise to the gradients or the updates communicated, there is like kind of a clear way how to like provide DP guarantees. Is it also kind of the, is it the same? Is it the same with this noise layer that you kind of like you can adjust noise and get the proper DP?
As the clients are distributed, so we do not have the control over what the other client's distribution is. So that's why we cannot control the bounds. So we need to limit within the local data, and that's why we cannot provide the overall DP guarantee. And that's why we said that only the calibrated noise is added to the activations, and that's it propagated throughout the model.
But you could still do local DP, right? Or no?
Okay. Yeah, local DP is possible.
Okay.
Yeah.
Thank you.
Thanks, Anna. So coming back to the Malfra concepts, we have the second component is the data that can be manual or automatic, whatever it's coming from the data consumer side. It will vet even the model, or it will vet the output, the results that we pass to the data consumers. So, sorry. So for these model sites, once it's vet, so it will keep into the model vault. So whatever goes into the vaults, it will be in encrypted form. And we have another component called earlock. So earlock is the instance. So the model comes with the containers, and then that container goes into the earlock instance, so which is secured by the secure enclaves, such as Intel SGX or AmTrust. So even the honest and curious IMT, they doesn't know. That means they don't know that what's happening inside the hardware and info the sensitive data. So we have the data custodians, which are, that means, distributed across the different locations or something, somewhere far from each other, and then they are agreed to engage into the model training. They definitely agree to some extent having the computational, the capacity as well as the vaults to maintain the data and models. So if the model is federated, the full model will be in the this yellow part on our left, which we can consider as a server part, and then this blue or green part as a client part. And if it is split, then split models will be inside into the model part. A little bit more into the Malfara system architecture. So the main idea is providing the security here is by isolation. And the isolation can be ear-locked, that means no connection at all. But to some extent, we try to provide the soft ear lock of the ear gaps in between these zones, various zones, right? So public zone is the model developer, which is connected to the internet, but these on the right-hand side, whatever we have in light brown and then the red, which has the data that's a sensitive, and the secure zone, they are not connected to internet, they're completely isolated. And then we control the message passing in between the public zone, that's the model developer, and then the secure zone, the computational zones, and then the data custodians is through this one-way message communications through the message queuing system. So it's only one directions of communications, and it provides the software lock in between these zones for the communications. And whatever it goes into the stack. Somebody needs to check the stacks and clear the stacks, and then the same for the message outflow to the other direction as well. And in the third zone, that's also the secure zone and the sensitive zone for the distributed, to enable the distributed machine learning, we have used the Kubernetes and Argo into our framework. So we do have the product in this, in the implementing the system. So if anybody is interested, please reach out to us. That means I'm happy to have more chat on these potential collaborations as well as commercializations. So this completes my presentation. Thank you. Happy to take more questions and in the discussion.
Thank you, Chandra. Yeah, so as a reminder, if you have any questions, please do raise your hand or just post your question to the chat and I'll try to unmute you. Yeah, so let me just start with kind of a more general question. So with respect to like combining federated learning and split learning, when it comes to theory, do you actually have any theoretical guarantees that this kind of combination will work? Or for instance, like do you have like especially like let's say that like the components that you've added, for instance, this like the noisy layer, that it's kind of like your model would still converge.
Yeah. So theoretically, theoretically we haven't analyzed it. So whatever we have done is based on the intuitions and the empirical analysis. So that's the way we demonstrate that this split-fed learning is feasible and has competitive, comparable performance to the split and split, federated and split learning.
And maybe one other question. So when you were talking about like split learning, do you consider each, so for instance, the part that is evaluated on each client, is it unique per each client or it's shared among the clients?
So in the split-fed, what happens is, in our that can set up an analysis. So each at the starting phase before starting the training, so all the clients have the same client-side models, right? Model persons, and and then once it starts training on the local data, the model will be changed. But at the end of each epoch, right? If they complete training on their local data, at the end of each epoch, then we aggregate it and then we synchronize to ensure that each client again have the same model at the start of the second epoch. Yeah, that's how it works.
So you always synchronize, right?
Yes, that's why we have the Fed server. So to maintain, that means at the end of training, we will have the one client-side model and one server-side model, and we combine, that will become my full model, fully trained full model.
So then there's a question from Shangjian. Let me try to unmute him.
Hello. My question is, if we implement the split learning and the federated learning, this expect the privacy benefits, do we get any performance improvements in this situation?
So are you referring to comparative performance of all three or just the split and federated?
It's just, just a common federated average or just a common split learning, which
federated and split, right?
Yeah.
So what we observe is it's really the data dependent, right? Sometimes the data have some characteristics. There are some correlations in between the the classes of the data, and it also matters on the the distribution, how it is distributed. So in this scenario, for particular this data set and this scenario, you can see with for an example, with the 100 clients, the performance of a split is quite better than the federated and split fed. So for the 100 client scenarios, though it's a bit noisy, but it converges very fast, and then it's a balanced scenario, right? But if you go into the little bit in the different clients for the higher rounds, the story is a little bit different. And if you go into this scenario, the story is much more different. So if it is extreme non-ID, then split is not converging at all. But somehow you can see it for 2 classes or 3 classes or 4 classes. To some extent, we have some sort of performance, or still, though it's going to the convergence, the split fed or the federated is doing more better than the split learning. So again, it's depending on the scenarios or the setups that we are analyzing.
Thank you.
Yeah. Thank you, Sean, for your question.
So maybe regarding with the previous question, do you actually have any intuition, like where essentially, like where or when split learning kind of shines, when federated learning shines, or when the combination of those two might be the best scenario, without actually looking into the convergence in the first place?
Yeah, so I guess I that answers that question, but I would like to again repeat that thing. So if we really want, that means higher number of, the clients, higher number of clients with each client having the low computational capacities, cannot run the full models, then in that case, Splitfed is the best option, right? If it is a single client with a few number of, the clients with maybe few number of clients, I can't exactly name the, that means say this many number of clients, but to some extent, if it is few, the overhead, we don't, consider, that means care about the overheads, then maybe split is okay with the requirement as the client cannot run the full. But if the clients can run the full models, then I guess federated would be the best.
Okay.
Yeah.
Thank you. And then there is one other question from Yahani.
Thank you, Mr. Samuel. Jahani, J.
Oh, sorry, Jahan.
No problem. Another question. I have analysis providing formal privacy guarantees for split learning is an open problem yet?
For split with how to say it, for split learning, or you're saying it's a federated or split fed?
Both.
Yeah. Guaranteeing in terms of, so again, I'd like to go back to this setup. Right? So are you referring to the client and main server side, or within the clients? That means among the clients. Maybe you are more interested. Yeah, maybe you are more interested in the clients and main server side, right? Yeah, as we discussed, because I left this work for a bit time. It's been a bit time, so we did this one work. But based on my, the experience, what I can say is at that time we had some difficulties guaranteeing the differential privacy guarantees for this distributed scenario. And I guess it's still open, but if we think it from the local differential privacy perspective, I guess it's to some extent it's been, the gap has been filled.
Well, could we measure the problem by the regret performance?
Maybe so. I have no, that means the expertise into this direction. To be honest, so I couldn't answer this your question.
Thank you very much.
Yeah.
Thank you.
Thank you, John.